Let's look at a technique for plotting the components of the frequency response. So I'm interested in plotting the magnitude and phase components of the frequency response of a system, and talk about a technique developed by Bode. The method is called, the corresponding graphs that we produce are called Bode plots. So consider starting with a transfer function in this form. There could be a gain term, and then we'll have a simple real zero term, actually a couple of real zero terms, and then we'll include a pole at the origin, a pole at B1, and then we'll include a second order term that would have complex, correspond to a complex conjugate pair of poles. Okay. So this has zeros at minus A1 and minus A2, and then poles at 0, minus B1, and then we could use the quadratic equation to show that there are complex conjugate pair poles at minus B2 over 2 plus or minus J square root of B3 minus B2 squared over 4. In the technique that we're going to describe, the first step is to actually rewrite h of s so that it's the constant term in each one of these expressions is equal to 1. So I want to factor out an a1 here, factoring out an a2 from this term, so I'll get, after pulling out an a1 and a2, then these terms become s over a1 plus 1 and s over a2 plus 1. And then similarly in the denominator, actually I don't have to factor out anything for the s term, but I have to factor out a b1 and then a b3 term, so that I'm left with s over b1 plus 1, and then I'll have here s squared over b3 plus b2 over b3s plus 1. So this is the first step, factoring out these constants, so that in each of my first and second order polynomial terms in S, the constant is equal to 1. The corresponding frequency response then, just substituting j omega n for S, would be, you don't actually have to do this step when you're producing Bode plots. We can work directly with the h of s expression, but and then here I'm going to write the one term first, and substituting j omega n for s. So this will be this first term here, just swapping the order of the terms. J omega over a2, and then here we'd have j omega 1 plus j omega over b1, and then finally 1 plus j omega b2 over b3, and then I'll have j omega squared over b3 as the final expression. I'm only going to talk about producing the Bode magnitude plot. Refer to your textbook for the technique for producing phase plots, but the magnitude plots are of most interest in the filter design, And here we're interested in the magnitude response. So I'm interested in the absolute value of j omega, of hj of omega. So again, this will be an entirely real function of omega. And I'll just take the absolute value or the magnitude of each of these terms that I had on the previous page. And in the denominator I'll have my s term, so just the magnitude of j omega. I had a 1 plus j omega over b1. And then finally, let me put little dots between these absolute values. I have 1 plus j omega b2 over b3 plus j omega squared over b3. And if we were to plot this for a given transfer function, and we'd have numeric values for all our a's and b's, to plot this by hand, still fairly complicated. It's not going to be easy, but on the other hand, if you take a look at plotting the log of the frequency response, and the convention is actually to plot 20 times the log of the frequency response. This will give us a graph in units known as decibels. Then the log of a product is the sum of the logs, so I'll have 20 log of this constant term and then I'll have 20 log of this first 0 term plus the second 0 term and then I'll be subtracting the denominator terms. The log of the ratio is the difference of the logs, so 20 log of j omega and 20 log of 1 plus j omega over b1, and then finally minus 20 log of 1 plus j omega b2 over b3. And in the Bode technique, we recognize that actually graphically adding components is a lot easier than can't even imagine trying to graphically multiply components. But if I can figure out how to graph, of course this is a constant term, but I've got some first order terms like this, 1 plus j omega, either over A or over B. If I can figure out how to graph those two components, or a component similar to that, or a component like 20 log of j omega, again if I had an s in the numerator I'd be adding a term like that, or these second order terms. If I can graph these individual terms, then perhaps I can come up with a technique that where I can add those together and get a complete graph of the frequency response in dB, 20 log of the magnitude of the frequency response, or a plot of the magnitude response in dB as a function of omega. And once I have that, I can easily pull out the gain and phase shift of our system with any sinusoidal input. So in the next video, we'll look at these individual terms and graphs of these individual terms.